Imagine a material that, when scratched or damaged, heals itself, just like skin closing a wound. This is not science fiction anymore. Self-healing biomaterials are becoming a major frontier in science, inspired by biological systems that continuously repair themselves without external help. These materials are designed not just to resist damage, but to actively respond, adapt, and restore their structure, opening new paths in medicine, robotics, infrastructure, and wearable electronics. So, how do they work? At the core of self-healing lies the idea of non-equilibrium systems, materials that are constantly exchanging energy or matter with their environment, allowing them to stay dynamic rather than static. Traditional materials are at rest once formed, but self-healing ones are designed to reactivate internal chemistry when disturbed. For example, some polymer gels contain microcapsules of reactive agents that, when a crack forms, rupture and flow into the damaged site, where they chemically bond and close the gap. Others use reversible chemical bonds, like hydrogen bonding or metal-ligand coordination, that break under stress and reform when conditions stabilize. But is it all just chemistry? Not at all. Biology provides an even deeper layer of inspiration. Living tissues use active repair mechanisms powered by metabolism, continuous input of energy to rebuild structure. Future self-healing biomaterials aim to mimic this with stimuli-responsive elements, materials that detect changes in pH, temperature, light, or electrical signals and initiate healing accordingly. Some materials include embedded enzymes or DNA-like instructions to guide the repair process, almost like a built-in blueprint. What makes these materials truly futuristic is their ability to maintain function even while healing. In soft robotics, for instance, flexible actuators made of self-healing elastomers can recover shape and movement after being punctured or cut. In implants, bioresorbable scaffolds can regrow bone while degrading themselves. This fusion of adaptivity and resilience marks a shift from passive components to active participants in function and repair. Why is non-equilibrium such a big deal? Because equilibrium means rest, no more change. But life operates far from equilibrium, constantly exchanging energy and adapting to stimuli. By moving away from inert materials toward metastable, energy-driven systems, these dynamic materials don't just fix breaks. They respond to wear, fatigue, or chemical imbalance, opening possibilities for materials that grow stronger with use or change their properties in real time. Is this practical or just theory? It's already starting. In 2023, researchers created hydrogels that can regrow nerve conduits, self-healing conductive circuits for wearable tech, and even concrete that uses bacteria to seal its own cracks. The challenge now lies in scaling these methods, integrating them into complex devices and balancing cost with functionality. The future may see cars that heal dents, phones that close scratches, or even spacecraft with biomimetic skin that repairs micrometeorite impacts. So why pursue this? Because self-healing materials point to a new philosophy of engineering. Not just resistance, but resilience. Materials that do not degrade and fail, but recover, adapt, and continue to serve. In this vision, we borrow more and more from biology, turning materials into ecosystems, self-sustaining, sensitive, and alive with potential. Self-healing biomaterials often incorporate dynamic covalent bonds, such as disulfides, amines, or boronate esters, that reversibly break and reform under physiological conditions. These bonds provide structural integrity, yet allow network reconfiguration when damaged. Under stress or cut, bond exchange reactions locally cleave and reconnect, restoring mechanical continuity. The kinetics of bond exchange can be tuned by pH, temperature, or catalyst concentration to optimize healing speed. Because the bonds continually equilibrate, The material maintains adaptability far from thermodynamic equilibrium. A hydrogel cross-linked, via imine bonds, recovered 80% of its original tensile strength within 2 hours at 37 DGC after being severed. It is like a zipper that unfastens under tension, but zips itself back up when you realign the teeth. Weak non-covalent host, guest interactions, such as cyclodextrin-adamantine complexes or metal-ligand coordination, enable reversible cross-linking and autonomous healing. These interactions are directional and selective, guiding polymer chains to reassemble at damaged sites. Upon network rupture, free hosts and guests diffuse and rebind, closing cracks without external input. The strength and lifetime of these complexes control the balance between material toughness and self-repair efficiency. Incorporating multiple orthogonal host-guest pairs yields hierarchical healing behaviors. A supramolecular elastomer using cyclodextrin-adamantine pairs. Fully healed surface cuts overnight at room temperature. It's like Velcro strips that detach under force but reattach themselves when pressed back together. Inspired by biological vasculature, synthetic biomaterials embed microfluidic channels filled with healing agents such as monomers, catalysts, or nanoparticles. When the material cracks, these channels rupture and release payloads into the damage zone. The released components polymerize or assemble to seal the breach, restoring functionality. Design of channel geometry and agent viscosity ensures rapid delivery and uniform distribution. Continuous networks can support multiple healing cycles by replenishing agents from reservoirs. A polymer composite with microvascular networks healed millimeter-scale cracks within minutes upon channel rupture and monomer release. It is like blood vessels delivering clotting factors to seal a wound in living tissue. Biomaterials can be engineered to contain immobilized enzymes that catalyze cross-linking reactions in situ when triggered by damage. For instance, horseradish peroxidase and hydrogen peroxide generate radical species that reform polymer bonds at cut interfaces. Enzymatic repair proceeds under mild conditions and offers specificity, minimizing side reactions. Enzyme kinetics and substrate availability dictate healing rate and extent. The spatial confinement of enzymes to the matrix ensures localized rather than bulk polymerization. A gelatin-based scaffold with embedded transglutaminase healed structural tears by reforming amide bonds within 30 minutes. It's like platelets, releasing clotting enzymes at a cut site to stitch a wound closed from the inside. Certain biomaterials leverage reversible phase changes, gel-sol transitions triggered by pH, temperature, or light to flow and fill damaged gaps before regelling. Upon stimulus, the network partially liquefies and flows into cracks. Removing the stimulus restores cross-link density and mechanical strength. These phase transitions can be tuned to occur only near damaged sites by designing localized triggers, such as heat generated by friction. Such materials combine fluidity for healing with solidity for load-bearing. A thermoresponsive polymer gel liquefied at 40 DC to fill incisions, and resolidified at body temperature within minutes. It's like wax that softens under warm light to drip into holes and hardens again in the shade. Living tissues maintain non-equilibrium states by continuously consuming metabolic energy to power repair processes. Synthetic analogs incorporate energy sources, like ATP, mimetic fuels, or light, to drive irreversible bond reshuffling. This active repair surpasses passive equilibration, enabling healing under load and in complex environments. The rate of energy consumption controls healing dynamics and frequency of repair cycles. Coupling energy input to damage sensors ensures on-demand activation. Such systems redefine materials as dynamic machines rather than static matter. A light-driven polymer used a photoacid generator to activate cross-linkers at damage sites, restoring mechanical integrity under mechanical load. It's like a self-charging battery that powers stitches to sew tears in real time whenever stress is detected. Mechanically sensitive chemistries convert applied stress into chemical signals that trigger localized self-healing pathways. Force-activated mechanophores embed into polymer chains and release latent crosslinkers, or catalysts, when stretched beyond a threshold. The released agents initiate polymerization or network repair exclusively where stress is greatest. This feedback loop tunes material toughness and extends lifetime by reinforcing weak regions preemptively. Designing mechanophore activation thresholds tailors the sensitivity and durability of the material. A polyurethane containing spiropyrin mechanophores released a healing monomer under 10 MPa of stress, sealing micro cracks without external cues. It's like a building whose structural sensors detect strain and automatically inject sealant into developing cracks, combining multiple self-healing mechanisms across length scales. From molecular bond exchange to macro-scale vascular networks, yields robust, multifunctional biomaterials. Nanostructured coatings provide first-line defense and passively heal superficial scratches, while deeper bulk networks respond to severe damage. Layered designs segregate healing modalities to optimize speed, strength, and longevity. Integration of sensing, actuation, and repair within a single material system enables autonomous maintenance. Such hierarchical architectures mirror the multi-tiered healing strategies of living organisms. A composite with surface supramolecular gel, subsurface microchannels, and core dynamic covalent network healed surface abrasions in seconds and bulk cuts in minutes. It's like human skin, which first clots small cuts on the surface, then remodels underlying tissue over days. Next-generation self-healing biomaterials will integrate real-time sensing, machine learning control of repair pathways, and programmable responses to complex stimuli. Embedding biosensors will allow materials to detect biochemical or mechanical damage and autonomously trigger tailored repair. Advances in synthetic biology may enable living materials that regenerate using cellular machinery. Coupling with wireless energy transfer could support continuous, non-equilibrium repair in remote or in vivo contexts. These innovations promise materials that adapt, learn, and self-sustain in dynamic environments. A prototype hydrogel with embedded fluorescent sensors and wireless heater arrays demonstrated on demand. Spatially precise healing guided by AI algorithms. It's like a smart wallpaper that senses a tear, calls its repair drone, and patches itself before you notice.